All right, so I'm going to talk a little bit more about expectation of random variables, yeah? So on Tuesday, we learned the following. So if you define the expectation of a random variable in terms of a Lebesgue integral, so it goes like this, right? So this is, so it has to be with respect to some probability triple, okay? And the Lebesgue definition, the Lebesgue integral definition for expectation of x is this. Although you note that, of course, in the first year, you would have something like this, right? This one generally be running like this for x. For continuous x, and okay, this is at the x discrete, right? This is for the elementary level, okay? You learn something like this. But now at this level, we look at it more generally. So we use the Lebesgue integral, yeah? So we're going to see how to use this result to so this definition to work out results, okay, that you would have obtained using this methods at the undergrad level. Okay, before that, so I think on Tuesday we work out one result, right? That the expectation of x is equal to the integral. Okay, this is the integral of tail probability formula. Okay. All right. This is for so this is for x continuous. Well, actually, maybe not. I would just say it's for non-negative x. Okay. Now it has a discrete version. So if x can take only non-negative integers, then your expectation of x becomes the integral becomes the sum. Okay. It starts from 1. All right. In fact, you can actually obtain this. This is actually quite easy to get from here. Okay, if you use this definition, it's actually easy to go from here because you look at this carefully, right? So clearly, okay, I should start it at 1 because there's no point starting at 0 because it will be 0 multiplied by something else, right? So start at 1. So start at 1, it will become something like this. If you start at 1, it basically becomes 1 times this, okay? And so on, right? Okay. And after that, you basically split this, right? So you see that over here, this is equal to px greater than or equals to 1, right? This 2, right? You take out the 1 and you group it with this sum, right? And then you also take out 1 and group it with this sum. So it will form to this one, okay? And then you take px greater than or equals to 2, right? Because once this 1 has been given over here, you are left with px equals to 2, right? But then you can sum the rest here, okay? So one of the guys here can go with this and pair up, so you get this, and so on. Okay, and therefore this is basically just this formula. All right. Okay, is it clear to you, the reasoning?
Yes, doctor.
Yeah, it's just basically if you look at it, it's actually quite simple because you're basically like allocating, right? You're allocating the objects associated with this probability. With you take one member and group it with this one. You take one member and group it this one, and so on, right? Then you will get this guy, okay? And then because it has donated one of it, so the next term you will start exactly at 2, right? And then you can then take, so this guy will donate 1 here, then you'll donate 1 here, donate, okay? So then you group together, you get this tail, and so on and so forth, right? So this is actually easier to get compared to this one. This one you need to use the Fubini's theorem, okay? Which I explained on Tuesday, right? So we have now these two results. You can use them. You can use them when necessary. Okay. Okay. Let's look at an example here. Now, suppose I have the probability triple with a Lebesgue measure on 0, 1, right? Then I define the following. X as a random variable is equal to 1, 2, okay? So, so we're going to find the expectation of X. All right. You look at this, take a pause for a moment and think about how you're going to find this.
Doctor, we can't hear your voice.
It's okay. I muted it. Because I have a lot of background noise at the moment. I was not saying anything. I was just drawing something. Okay, right. So basically, so you define this random variable. So random variable, by now you know that it's actually a set function, right? It takes values in, just to recap, your x is a function on omega and maps it to some image, right? So basically over here is just your this is, you treat it as a function like much you will treat it as you write f, right? But in probability we write x for random variable, and you have to think that it is actually a function, yeah. So it's basically writing something like f of omega equals to 1 and 2, which you are very familiar with, right? But or that one, if you look at it from a graphical point of view, right? Later. Okay, but if you, with respect to the probability triple, basically, so is you have your sigma field and then your omega. So basically, you take your function x, you take this segment, right? 0 between 1/2, you take this and you map to 1, right? So that means any value that you get, all values between 0 and 1/2, you will map to 1, right? And all values between 1/2 to 1, you will map to 2, okay? And then in order for it to be assign a probability measure, there must be some kind of inverse mapping to the sigma field, right? So you have the inverse mapping here, right? You take, so this set here is equivalent to the, you come here and then you take the inverse mapping of 1, which goes to some set in F, right? And since this is 0, 1, so this is a Borel sigma field. The Borel sigma field will contain all these intervals, right? These intervals. So you map it to 0 to 1/2 because it says it's a Lebesgue measure on 0, 1, 2. So it's basically sorry, 0, 1. So it's basically measuring the length, yeah. It's basically measuring the assigning a measure based on the length. So these are lengths, and your one maps back to 0, 1/2, and this one maps back to this interval 1/2 to 1. Okay, and therefore you can assign a Lebesgue measure, right? So the Lebesgue measure of 0, 1/2 is simply 1/2, right? The length. And the Lebesgue measure of 1/2 to 1 is simply 1/2, right? So basically what happens here is the following. So when you see this integral, right? Now make a sketch here. So this is your x, right? It says take value 1 if omega is between 0 and 1/2. So you have this interval, right? So this 1/2. So it takes a value of 1. So 1 is here. Okay, of course, to be precise, it doesn't include this endpoint, right? They come until here. And then takes value from 1/2 to 1. Okay. Someone is trying to get in. Is she in already? Just a moment. I don't see anyone in the. Let me see participants. I can't see the participants. So strange. Oh, okay. Just a minute. Okay, okay. Already admitted. Right. All right. So then you have this function 2 here. So starts from here and goes all the way here. So this is 1 and this is 2, right? So basically you have a function like this, okay? This is your omega, this is your x omega. Right, so basically your x is playing the role of a function here, right? Right, so now it's clear. So if you're going to evaluate this Lebesgue integral, right? So you notice that this is a measure, right? Okay, so it's applying a measure on your values of x. So these are your values of x here. So basically this involves the area under the curve, right? The Lebesgue, so this is basically just the Lebesgue integral of this function, okay? So, and this is very easy to do because then you basically the Lebesgue measure is you find so for this set, right? So you have a set here, right? So this set, since you're applying a Lebesgue measure on it, so the measure is 1/2, right? Okay, so the measure is 1/2 and you multiply with the height here. Of course, here you are taking the infimum, right? Over all points, but since it's a flat line, the infimum is just the value itself, right? So multiply by 1. Then plus this measure, okay? The measure here is 1/2. Then you multiply by this height here, okay? So this height will be 2. So you end up having 3/2. Okay. Now you can double check on this that this is 3/2. Now at the undergrad level, this is what you will see. Okay. Instead of giving you something like this, you never see this in the undergrad. I mean like first year, they'll give you something like this. Okay, which you are familiar. They will just say that, oh, you define a Prodi mass function on these 2 points with these values, and then find the expectation of x. So in this case, what you would do is you basically apply the definition. So you will do it something like this, right? Which you get the same thing. Okay, so at the undergrad level, when they show you something like this, it actually means this. Okay, but of course, this is going through all this at first year is just not possible. Yeah, the material is too abstract, so students will not be able to learn it. Okay, but for this, I think people are okay, right? So intuitively, you say that there is actually there's actually a probability, a measure. You give the measure. It never properly explain where you got the measure from, right? It's just some number. So now you know that you're applying a measure on, in this case over here, you get the measure from a Lebesgue measure on the unit interval. All right. So, so now you have, this is actually the proper way to do things, all right? But this is too abstract for most people. So generally it is simplified into this form, right? I mean, at the end you get the same result, okay? But this one is if you think about it high enough, there are many unanswered questions. Right? Okay. So what happens if you have something more involved? Okay. Let me clear this. Okay, suppose you have something like this. One, two, three, right? This is omega is a rational number in 0, 1. This one is some kind of irrational number, 1 over I. So this is definitely irrational, right? Because pi is transcendental, so this is irrational. This is irrational. And then you have this is all the other numbers, right? The set of 0, 1 without this. Okay, so basically these are your rational numbers, and these are your irrational numbers. All right. So then you want to find expectation of x. Okay. Now, so again, this is xdp measure on x. So you sketch this from 0 to 1. Now, actually, this is not sketchable. As you know, this function, right? Where you basically you come across this before, right? The indicator function for irrational, so for rational numbers, it's basically an unsketchable function because it's full of holes. But anyway, we for just to get an idea, not to say that this graph is correct, but because you basically can't sketch it, but it's still useful to make some sketches. So this will be 1, right? 1 is rational, so there are many rational numbers here, right? So it'll be kind of like all over it, right? 1. So basically, you know that there's something like here, right? For this set here, so this is all rational number. Then at a particular value, 1 over pi is about 0.3, close to 1 over 3, somewhere here. And this value you have 2, just 1 point, right? And other than that, you have 3, basically, which basically like all the irrational. So these are your irrational numbers, right? So at the irrational numbers, you have your 3. Again, it's full of holes, right? Because the holes have been dug out from the rational numbers, and there are infinitely many of them. So basically, it's like also full of holes. Okay. Now you're going to evaluate this expectation. So let's see what happens. Now, so you have to look at the measure, right, on the sets here. Okay, look at the first one. The first set, right? So let's say this is the A1 set, this is the A2 set, and this is the A3 set, right? What is the measure on the A1 set? The measure over the set of rational numbers in unit interval. What is the measure? Anyone?
0.
Yeah, right. Okay, because it's a countable set, your Lebesgue measure of a countable set in unit interval is 0. And since this measure is 0, right, and for Lebesgue integral, you're going to multiply with the infimum of this height. Then since this is a constant, your infimum is basically just that value. So you're multiplying basically for the first component here, but you're basically multiplying 1 with 0, right? Because the measure for the set A1 is basically 0. So done with the first part, then the second part is this point, right? At this point, you have What's the measure of singleton?
Zero.
And 0, right? Okay, great. So it's a singleton, the Lebesgue measure is 0. And you're multiplying with the value here. There's only 1 point, so the infimum is itself 2. And then finally, you'll have the third component, right? So third component here, your set is the set of irrationals, right? What is the measure here? What is the measure of this set? Okay, great. The measure is 1, right? Because this is the unit interval without the countable set, right? So when you measure this is 1. All right, the measure is 1. And then you are multiplying with the infimum of these things here, so it's 3. So the answer here is 3. Okay? Right? Now, you will have a very difficult time if you try to translate this situation to the first year undergrad. Well, you will have to maybe do something. Let's try if we can do it. You basically will have something like this. 1 when your x is this one. And then 0 measure for x in Q intersect 0, 1, union 1 over pi. Okay, you probably will have to write something like this, and then if you ask people to find expectation of x, it will be difficult for the students. If let's say you think about yourself as a first year student, you see something like this, and I ask you to find the expectation of x. How are you going to do this? Looks unclear, right? Because it looks unclear because if you're going to use the integral to do it, the Riemann integral, because you only have Riemann integral as your tool, right, for first year. So you'll find it strange how are you going to do the Riemann integral for this thing here? Because you don't know what is the so in that case, I think in that case, yeah, in that case you are not even sure, right? You're not even sure whether this should be a P or for discrete or an F for continuous, right? So in fact, the framework that you saw just now, right, like this kind of framework, it only works for very well-behaved kinds of situations. But once you start to have this sort of more general situations where you need to look at countable sets, things like that, it's not so straightforward, right? But with the correct framework like the Lebesgue integral, then you can do this very easily. Okay. All right. So is it clear to you for this example?
Yes, doctor.
Okay, maybe I also show another example here. So a special case, indicator, random variables. right? So let's say we have I. This is a random variable I, and then you have basically a condition. Okay, so this is actually a condition. So this means that it is equal to 1 if omega is in A, and 0 if omega is not in A. Okay, so basically, yeah, so it's very simple. So let's say, so suppose your A is an interval 0, 1 over 2. Okay, so say 1 over 2 here, right? So between 0 and 1 over 2, it will be 1. And outside of that, it will be 0, right? It's just an indicator function. So the function is just like this, right? So this is your I, A, this is your omega. All right. So this is one way to think about it. And therefore, if you find the expectation, right, of let's say I WA, you go by the definition of the Lebesgue integral, it will be just like this, right? P over omega. So basically, then it is just the Lebesgue integral of this function, right? And this function, this is 1. So the Lebesgue integral is, so this doesn't matter, right? So basically, this is the, you basically have the measure. The measure here is 1 over 2 multiplied by 0. And the measure here is 1 over 2 multiplied by the height here, 1, right? So in this case, you get 1 over 2. More generally, you will have some general set, right? So let's say your A will be some particular measure, let's say 0 to something else, C. And the measure here, right? So you'll be C, okay? So the measure here will be, so I will put a measure here. So this will be my P of the measure of the set A, right? Yeah. So this consists of all the omega falling in A. So basically, this is a measure on A. This is a measure on A complement. Okay. So basically, in general, therefore, expectation of the indicator function is just since this is 1, you multiply the Lebesgue measure that, so you have PA. All right. So this is an important result. The expectation of an indicator function is given by the probability measure, right, of the set of interest. So similarly, if your condition here is like, for example, something like this. Let's say you have a condition like this. So this is equal to P of, so this is the condition, right? So therefore you have this. Okay? All right. So so now that we know a little bit more about expectations, so then we will look at maybe we have a bit of time to look at an example of inequalities. inequalities involving expectations of random variables. Okay, so for example, you may have, so I'll develop one example called Markov's inequality, which is an important inequality, which goes as follows, right? So let's see. So this is your x, omega, right? This is your omega. Okay. So this line here is basically just your line x, right? Now, suppose you have some cutoff here. Let's say this is alpha. So you can think of it like this. So at this alpha, so over here, this is also alpha. So I'm thinking about this. So this result is actually has a geometric basis, right? So basically, I know the following. So now I know that the expectation of x, okay, is actually greater than or equals to the following: the expectation of x, indicator function x greater than or equals to alpha. Okay, so let's look at this carefully. Actually, maybe I do not put the expectation first. Let's just look at it from a geometric point of view. Okay, now so this x is this line here. Okay, it is larger than x multiplied by this condition. So what is this condition? X multiplied by this condition is this line. Go like this. And at this point, when your x is greater than or equals to alpha, then it becomes, afterwards it becomes this line. Okay, so this thing here is this blue line. Okay, it goes when your x is below alpha, is 0, and once it reaches alpha larger, it just becomes x, right? So it's this line. Okay. All right. So clearly, you can see that the black line, right? So the black line here is definitely greater than or equals to the blue line, right? Agree? Do we agree on that? So first, let's go back to this again. I just want it to be very clear to everyone. So this inequality is purely based on geometrical considerations, where your x is basically this line, all right? And this is definitely larger than x multiplied by the indicator. So this is basically when you have x multiplied by an indicator, it just means that this thing is 0 when x is less than alpha, right? Which is flat. Once your x starts to be equal to alpha, it becomes x, right? So that means this line, right? So definitely your black line is larger than or equals to this blue line, right? Okay, can everyone accept that?
Yes, doctor.
Yes, doctor.
Right, okay. So I think the geometry is actually quite simple. And then if you could continue to do an inequality, what would you do? Okay, so you basically compare, right? The black line is larger than the blue line, right? And the blue line is larger than what? Anyone? From the diagram here, the blue line is larger than what? What line?
The red line.
Yeah, that's right, right? Geometrically, it's the red line, right? So what is this red line? How would you express this red line? How would you write it down over here? Using indicator functions. Anyone?
Actually, doctor, that the indicator function, right? Is that a 1 or an I as a notation?
Yeah, you can write it like this. Sometimes it's written like a big one. Okay, they are the same thing. In some books, you'll see they write an I. In some books, you'll see that they write some one that is a large one, like or sometimes bolded. Anyone? How to express this function? This flat line here goes from 0 to alpha 0, and then after larger than alpha, you become alpha. So how should you express this?
Is it I with a condition x greater than or equal to alpha?
Is it just like that? So this will be 0 or 1, right? So what is this value?
Or times alpha, sorry.
Right, okay. So correct, right? So this red line is this thing. Okay. Therefore, if you take expectation on So you start from here, you come until here, right? So you take expectation on both sides, you will get expectation of x greater than expectation of this, and this is greater than expectation of alpha this, right? And this is equal to alpha probability of x greater than or equals to alpha, right? Because we just look at the meaning of expectation of an indicator function, right? So you have this, and therefore your p of x greater than or equals to alpha is bounded by expectation of x over alpha. So this is your Markov inequality for non-negative x. Okay, in this case is a non-negative, but you can generalize it to to all real x, right? Later we will see that, right? But this is the first result for Markov's inequality. Okay. If you, so this will also hold if you replace right, if you replace x with x squared, right? So this will also hold, so you will have basically you will have p of x squared, right? You just replace x with x squared, so you will get this. And then if I replace further x with x minus mu, yeah. All right, that means I kind of like replace it with the centered form, right? Subtract mu, then I will get this. Let me see. Oh, okay. So I have to square this as well. It's basically like you square you square everything here. So let me see. Not really. Let me see. Okay, right. So I find, okay, so it should be like this. So actually the square will come out from here. But this part, there's nothing here. So I'll explain a bit later. Right. Here. So over here, this will be your variance of x and over alpha squared, right? So this inequality here is known as the Chebyshev's inequality. I think you have come across it at the undergrad level. Maybe sometimes they teach it in some textbooks in first year statistics. Sometimes talk about it. But actually, it's not very useful for actual work. It's just useful work for theoretical results, right? So you have another inequality called Chebyshev's inequality, which you can get from Markov's inequality. Now, why does this square actually come out? Actually, if you fall back to the geometry, you can see why. Let me clear this. So the geometry now is instead of x, right, I have x squared. So my x squared is like this. Okay. So this is above some value alpha, right? So this will be alpha squared, okay? So again, I do the same thing. And then I have the blue line here, which is this. Right? So definitely your x squared is larger than or equals to the blue line, which is x squared indicator function x greater than or equals to alpha, right? Blue line. And the blue line in turn is greater than or equals to the red line, which is indicator function x greater than or equals to alpha. But here, since this is x squared, so this will be alpha squared. Okay? You take expectation on all sides, you will get. Okay. Sorry, this is x squared. Yeah? Wait, let me see. That should be. Let me see. It should be. Should be x. Let me try this. The expectation you get alpha p of. So should be x squared. So bounded by this, okay. All right, okay. So let me check this again. I think I may have made some mistakes. Not really. So no, I think I've made a mistake. Clear this. So you've got x, if you've got x squared, it's like this. Say this is alpha. So this will be alpha squared, right? So okay, let's look at the geometry carefully. Say x squared. So x squared will be larger than the blue line. So x greater than alpha. Okay, let's think of it like this. So I have all right. Okay, so I think this is the appropriate one. All right. So let's start again. So you have x squared is this curve here. Now is this black curve here is larger than the blue curve, right? The blue curve, you have two parts here between alpha and minus alpha is actually 0, yeah. So this condition, we know that this means x larger than alpha, union x less than minus alpha, right? Which basically are these two parts, okay? So at these two parts is x squared, but outside of that is basically just flat, all right? Okay, so this is correct. And in turn, this blue line is greater than this red line. And this red line occurs at alpha square I absolute x greater than alpha. And therefore, you take expectation on both sides. It will be okay. And therefore, my probability of x greater than alpha is bounded by expectation of x squared over alpha squared. And if you replace x with the centered version, where mu is expectation of x, yeah, then you have the following. Expectation of x minus mu squared over alpha squared. And this is a variance of x over alpha squared. Okay. Yeah. So please ignore the derivation that I gave you 5 minutes ago. That was not correct. So this is the correct one. This is called the Chebyshev's inequality. Okay, and the geometrical argument is based on here. Right? It basically is just comparing curves and see which one is larger than which one. And I think the part that is new to you is the use of indicator functions like this to flatten out certain parts, right? But this is actually quite useful. Using indicator functions together with random variables can actually help you control, right, certain things. Like for example, certain parts where you want to flatten it to 0, you just multiply it with an appropriate indicator function, right? And you can derive many useful results using this approach. Okay, so this inequality is very useful later when you study convergence. Convergence in probability. Okay, so this comes from expectation, yeah. All right, okay, so I think I've used up a bit of time from the tutorial session. So let me stop here and let's take a 5-minute break and then we come back for the tutorial, right?
Okay, so can everyone see my screen?
Yes.
Yes.
Okay, so Question 1 asks us to find the Lebesgue integral of the function fx equal to 1 if x is irrational numbers and fx equal to 0 otherwise, or we can say that if x is rational number over the interval 0 to 1. So the Lebesgue integral is given by the formula below. And we know that the infimum of the function fx equal to 1 is 1 and fx equal to 0 is 0, since it's just a constant line, right? So now we need to find the Lebesgue measure of these two sets. So let A1 equal to the set of irrational number and A2 equal to the set of rational number. So A1 is a set of irrational number in the interval 0 to 1. So the set is uncountable, hence the Lebesgue measure of A1 is equal to the Lebesgue measure of the interval 0 to 1, which is 1. And A2 is a set of rational number in the interval 0 to 1. So the set is countable and it can be expressed as a countable union of a singleton. Therefore, the Lebesgue measure of A2 is equal to 0. So by substituting the Lebesgue measure into the equation 1, we get that the Lebesgue integral equal to 1. Did I do it right, Doctor?
Yeah, it's correct. Okay, thank you.
Okay, thank you, Doctor.
So the thing here is to note the measure, right? Because since your function is actually a constant, so that's taken care of. So you just need to evaluate the measure of the two sets, right? And yeah, so yeah, so since you know that the countable set has 0 measure, so the other set the other set is basically just the similar to the its Lebesgue measure is equal to the Lebesgue measure of the unit interval. But maybe I show a bit how to write it in a more formal way.
Okay, thank you, Doctor.
So basically, you want to find the you can write mu or lambda, doesn't matter, right? It's just a measure. So you want to measure the set of 0, 1 without q in 0, 1, right? Okay, you're so interested in this set. Now we start as following. To measure this set, first we know that our 0, 1 set can be broken down into this easily, right? These two sets are disjoint, right? This and these are disjoint, right? They will never overlap, right? Agree? Okay.
Yes.
So the idea of writing, if you write a set as a disjoint, as a union of two disjoint sets, the advantage is that when you put a measure on it, you can decompose the measure that's the disjoint sets, right? So the disjoint sets, when you put a measure on them, is just the sum of the two respective measures. So therefore, lambda of 0, 1 is basically just lambda of this plus lambda of that, right? Because they are disjoint, right? So they can split them. And since you know this is 0, countable set, and you know that this is 1, therefore you can rearrange and you can find your lambda, okay? Although it's correct that you got the correct measure, but more formally we establish it using this relationship, okay? Because these two things we know very clearly how to calculate it. All right. So and then since you already know these two, then you will know this one. Okay. All right. Okay. Then we move on to the second question. Nor Emir.
Okay, Doctor.
You share your screen.
Okay, for question number 2, the question is let fx equal to 1 over 2 for 1 over 2. Fx equal to 1 for 1 over 2, x to 1. Fx equal to 0 for x is rational number in 0 in 1 is 0 to 1. Find the Lebesgue integral of f with respect to a measure mu. Okay. We do the graph. So this is the graph, and this is the formula mu a1 times increment fw. W is in a1. So we know that x is in rational number. So rational number with increment 0. So q is a countable set. So mu a, the Lebesgue measure for a1 is 0. So for the two interval, 0 to 1 over 2 and 1 over 2 to 1, the increment is 2 and 1. And the Lebesgue measure is 1 over 2 and the Lebesgue measure is also 1 over 2. So we plus all this 1 over 2 times 1 over 2 plus 1 over 2 times 1 and plus 0. So we get 3 over 4.
Yeah, okay, that's right. Just a minor thing, the notation. I think when we write the integral, right, for Lebesgue integral, we generally do not write the limit of integration from 0 to 1. That is more like a notation for Riemann. Usually we will just put a set, like in this case, you just put the set 0, 1 at the bottom.
Okay.
Yeah, it's just a notation. I mean, it doesn't really affect the answer, right? Okay. Yeah, that's correct. Okay, let's have question 3 presented. So yeah, Nurul will present on behalf of Farah, right? Because she's not able to be here. This is her recording, right?
Yes. Can you guys hear the voice?
No, I can't hear it.
What about now?
No, can you hear it?
Yeah, I can hear it, but
Oh, you can hear it on your computer. Oh,
yeah.
then okay. I see you have to. Are you using a headphone?
No.
You're not using a headphone.
No.
You're using a microphone. Oh.
Yes.
Okay, maybe yeah, because it's taking the signal from your microphone. You see, so unless you put the microphone to the speaker where it's reading out this thing, otherwise it may not be able to. We may not be able to hear it. Maybe you can try that.
How about now?
Yeah, I just put your like microphone close to the speaker where it's reading out this thing and see if it works.
Oh. Give me a moment.
Yeah.
Doctor, should the next person present first? Because I need to figure this out.
That feels strange also, right? Usually when you share something, yeah, it should be able to play. I don't know. Without doing the hack that I mentioned just now, so it feels a bit strange. Okay, never mind. Maybe just put on hold for a while. Maybe we move on to the next one first. Okay.
Okay.
Najiha, is it? Question 4.
Hello.
Yeah. Okay.
Okay, for problem number 4, the question asks to use the Lebesgue-dominated conversion theorem to evaluate the limit of n sine x over n over x times 1 plus x squared from negative infinity to infinity. So the first step that we need to use is need to show that the absolute fn is bounded by function of g almost everywhere. So we let fn is equal to n sine x over x times 1 plus x squared. So we calculate the absolute of fn. So I pull out 1 over 1 plus x squared because the function itself is already positive. And then since absolute of sine x is less than absolute of x, we apply that less than equal to x over n over absolute x over n times 1 over 1 plus x squared. And then we get that 1 over 1 plus x squared is gx, where gx is integrable function and it is a dominating function. And then we need to show that the limit of fn is f as n approach infinity. So we calculate the limit of fnx. So here, I calculate the limit of sine x over n, and we know that the limit of sine x over n is equal to 1, and then we get that the limit fnx is equal to 1 over 1 plus x squared, which is equal to fx. And then from that, we can calculate it by dominated conversion theorem. So we use the interchange of limit and integral, and the integral of limit n sine x over x times 1 plus x squared is basically from up here. It is 1 over 1 plus x squared, and the integral of 1 over 1 plus x squared is equal to arctangent of x. And from here, the limit is from negative infinity to infinity is also equal to 2 times of integral 0 to infinity. So then the answer will be pi.
Yeah. Okay. So yeah, I think that is correct. Okay. The steps are correct. So you just to check the integral, that's arctangent. Yeah, it's pi. Yeah. Right. So the trick is to find the function g, right? So that's the dominating function. It turns out this dominating function is 1 over 1 plus x squared, and it's definitely integrable to arctangent. All right. So yeah. So you have to use some inequality related to sine of x over x. Okay. Some inequalities related to the sine function. Okay. So basically, this is just to check that you interchange the limit. It is valid, and you do get some results. Because if you don't interchange the limit, right, it's very hard to do, right? If you try to integrate that integral with the sign thing inside, oh, you get a, maybe it's not even integrable but analytically. That means you may not have a closed form solution. Anyhow, it looks very hard to do, right? So if you try to integrate it first, it's too difficult. But you're not really interested in the result, the integral, because you're gonna take limit anyway at the end, right? So it is nice that you can move the limit inside, and you show that you can do that because of you satisfy the requirements for a dominating function, right? Okay, thank you, Najiha.
Okay, Doctor.
Okay, Carmen, you want to share your screen?
Hello, doctor. Hello.
Yeah, go ahead.
Okay. So for the question 5, we need to use the Lebesgue-dominated convergence theorem to show that it is equal to the CDF of the standard normal distribution. So so firstly, I define we have to find a G, which is the absolute of Fn is smaller or greater than G almost everywhere. So I set my G equal to 1 over 1 plus t squared. And then it is, I show that it is integrable. And then the Fn is also converged to F, which is 0. And then therefore I can interchange the limit and the integral. So I will, then after that I do the limit, and then I will get the last line, which is the normal, the CDF of the standard normal distribution.
What is your, okay, I mean, if you just simply move the limit inside, of course you will get you will get this result, okay, because the limit is not hard to do, because the hard part has already been given to you, that limit, and then the other one is just basically using exponential function, right? So okay, but your choice of dominating function is a bit there are some problems with your dominating function. You use 1 over 1 plus t squared. This is actually a special case of, if you notice carefully, this is something like a special case of your t distribution with 1 degree of freedom. I think if you put your n equals to 1, yeah, if you put your n equals to 1, it is, yeah, but almost the same. Does it really dominate?
If the Fn is very large, they will exceed the G a little bit, and then after that at the tail they will converge to 0.
Okay, I will give you an argument why it doesn't dominate. Okay, your 1 over 1 plus t square is it is very it's very flat, right? So as your degree of freedom increases, the peak will increase. The peak concentration around 0 will increase, and that surely will already escape from your 1/1 plus t squared. So yeah, you have to do something more about it. Okay, it's okay. Let me handle this from here. Okay. Okay, thank you, Carmen.
Thank you, Doctor.
All right. So basically, that one is the density function of the T distribution. You know that the T distribution, right? Is a more general form of your. We know that the T distribution will converge to the standard normal as the n goes to infinity. But at n equals to 1, it's really a very flat. Actually, when n is equal to 1, your T distribution is a Cauchy. Is equal to a Cauchy distribution. You can check that it will equal to its density will equal to this, n equals to 1. And then when it starts to increase, right? You can see that the tail, right, is actually fat because there's a lot of uncertainty, right? When your sample size is small, a lot of uncertainty, so the tail is very fat, right? But as you start to have n equals start increasing, it will start to concentrate. Your T distribution will start to concentrate like this. Right? And in the limit, it will become the normal, which is like this. Maybe just like this, the normal. Okay? So it will become closer and closer, right? Closer and closer to the normal. Now, you use this as a dominating function. It cannot be dominating because it can't be dominating because you choose your n to be more than 1 already. It already cannot dominate this part, right? This part is already getting out of your function. Okay. Now you think about this carefully. You can still use this guy, but you still use this guy, but you can you think of it? Use this guy, but try to do some scaling. Just scale it a little bit, or maybe how would you kind of just scale it a little bit so that it actually will come to dominate all the other all your Fn. Do you see how to do it? So it's this curve. So you do something on it so that all these other curves, right, will sit beneath it, and then still that function is integrable.
Leave the graph, like change to another y-intercept with a plus.
Change to another y-intercept. Oh, okay, but you said lift it, right? Yeah, lift, right? So lift it where? Take this guy, this purple curve, and lift it where? Okay, above the red line. All right. So basically, you lift it up, right? So basically, it will the same thing. You lift it up here. How is this lifting achieved? This point goes to this point. This point goes to this point, right? This point goes to this point. So there is a proportional kind of lifting, right? So how do you lift it?
Function plus with some real number.
Plus?
Plus with some numbers, some integer to lift it. You see?
Okay, you can plus. Yeah. Well, if you want to preserve the shape, right? You can just multiply it with a constant, right? You times a constant where your c is larger than 1. You just pick any c so that this will be lifted clearly above, right? So you don't have to decide what this particular c is. It's just some c that will lift clearly out up here and dominate the rest, right? Agree? You cannot use the other like n equals to 2. Like n equals to 2 will be something like this. If you leave n equals to 2, it will still lose out to this n equals to 1, because n equals to 1, the tail is really flat. Your n equals to 1 is dominating at the tail already, so you should use this n equals to 1 case. So you lift it. So basically, your dominating function is equal to c of this. In fact, you don't need to write the pi because that will go together with the c already. Just to make it simple, your dominating function is c of a constant multiplier of 1 plus x squared. All right. Okay. And so c suitably chosen, right? Such that c of this is dominating your Fn. Okay, so this is clear. Just lift it up. And is this integrable? Yes, of course it's integrable, because you integrate this, right, from minus infinity to infinity. It's basically equal to well, if you keep the pi here, right? Okay, maybe it's easier to keep the pi there. You keep the pi there, then this will be c, right? Because the PDF here is a Cauchy probability density function which integrates to 1. You're just multiplying it with c, so it's integrable. Okay, so this is the idea. All right. So is it clear to you how to construct this dominating function? Carmen, is it clear to you? Okay, so basically you lift it up, right? So that's why I have been emphasizing a few times already in the course. If you study this kind of problems with keeping in mind all the time about geometric intuitions, right? You can solve a surprisingly large number of problems using this kind of approach, right? Think about the problem from a geometric point of view. If you get stuck, all right. Sometimes if you think of it analytically, it's okay. Like just now, the case involving the sine x over x, right? That's fine, right? Because you are analytically thinking about the bound for sine x over x, right? But in this case, I think because the function is looks complicated, so you will need to but it's not hard if you can think of it from a geometric point of view. Like in this case, if you do some sketchings, then you probably have some idea already to do the lifting. Okay. All right. Okay. So let's go to the last problem. Let's hope the problem has been fixed.
Firstly, I state the definition of almost everywhere, which state that a property of X is said. Okay, for problem 3, let f be the Lebesgue integrable with respect to measure mu. Show that if f more than 0, then integrate f in respect of d mu is equal to 0, then f equal to 0 almost everywhere. Firstly, I state the definition of almost everywhere, which state that a property of X is said to be almost everywhere if the set point in X where this property fails is contained in a set that has a measure 0. Okay. Given f more than 0 and integrate f in respect of d mu equal to 0, as we know that the integrate of f in respect of du is a Lebesgue integral. Let fn be an increasing sequence of simple function converge to f. It follows that integrate fn in respect of d mu is equal to 0, which is the Lebesgue integral of fn equal to 0. Okay, let f equal to x include 0 to infinity such that fn x does not equal to 0. There exists mn include in summation of ai with measure mn equal to 0. Implies that fn x equal to 0 for all x does not equal to mn. Then let m equal to union of mn, then m include in summation of ai with measure m, which is less than equal to summation of measure mn. As we know that measure mn is equal to 0, since x does not equal to m, this implies that fx equal to 0. Hence, f equal to 0 almost everywhere.
So yeah, that's the end of her presentation.
Okay, thank you. So I think the presentation is maybe slightly abstract. So let's try to look at it like maybe I always like to approach these problems like maybe more visually. It's easier to understand. You have these equals to 0. And show what? Let me check it. Can somebody fill me in? What was the condition given?
F greater or equal to 0.
F.
Greater or equal to 0.
The condition, what was the condition again? There are two, right? Okay. Never mind. Let me just check the.
It said let f be a Lebesgue integral with respect to a measure mu. Show that if f greater or equal to 0 and integral of f d mu equal to 0, then f equal to 0 almost everywhere.
Oh, okay, okay. Where am I? So f equals to 0 almost everywhere, is it?
Yes.
Okay, so I think f is greater than, what was it again? I'm trying to look at, okay, where did that go? Just a minute. Okay, let f be Lebesgue integrable with respect to a measure mu. Okay, fine. Show that if f is greater than or equal to 0, and then f integral of f d mu is equal to 0, then f is equal to 0 almost everywhere. Okay. Okay, so basically, okay, you look at it like this. You want to show f is equal to 0 almost everywhere. That means except at certain points, right? It means your f can be non-zero at some points with zero measure. Okay, so let's see. Now your f, it says f is greater than or equal to 0. So it's some value that is maybe up here or something. Could be some situation like this. Some values like this. Maybe some values like this. Okay, maybe this is a 1, maybe this is a 2, or whatever values, right? So it can be like this. Okay. But then this, so the situation is like this. So then you have so you have so this is f equals to 0, right? And okay, so your f is going up like there are some examples like this. So, but then you basically define, right? So you define f to be greater than 0 at sets A1, A2, whatever, where mu of AI is equal to 0. Okay, and then you define f equals to 0, where at sets B1, B2, and so on, where mu of BI is greater than 0. Okay? Right? So basically, so this corresponds to this kind of situation, right? And with this two situations, definitely your integral of f d mu is equal to 0, because when it's greater than 0, you basically have a 0 measure, right? So 0 multiplied by this f is 0. And then for those sets where your measure is non-zero, but since it occurs at f equals to 0, so the infimum is 0. So multiplied by a non-zero, you still get 0. That's how you can get your integral of this, right? Okay, and because of this, right, this fulfills the condition of f equals to 0 almost everywhere, because by definition, almost everywhere, it means your f is not equal to 0 at some points, but with 0 measure. Okay, so it's just basically this question is just basically trying to reinforce the learning of the term almost everywhere, right? I hope this is actually more straightforward, maybe. Of course, you would need to watch the video again to be of the presentation just now to be maybe more careful with the statements made. But I think generally it's just you can construct an example like this to show f equals to 0 almost everywhere. Okay. Okay, is it okay for you, this example? Right, it's just to have some exercise on the term almost everywhere so that you don't forget about it. All right, what exactly does it mean when you say almost everywhere? Okay, so that's why if you have f equals to 0 almost everywhere, you integrate it, you're going to get this 0 lah, right? If you have okay, let's keep it simple in this case because I don't know how it ranges. Okay, it is definitely 0. Okay, so all right, so that's all all we have for this tutorial. We don't have a tutorial. We take a break from one tutorial for next week to catch up on some material. All right, so we will have tutorial 5 the week after. All right. Okay. So that's all for today. Thank you for your time, and I'm going to
Thank you, Doctor.
yeah, stop the recording now.